Hello friends, welcome back to my YouTube channel Programming in My Way. Today we are going to discuss very important tree, that is AVL tree. So in this lecture we are going to see AVL tree in data structure. So we have covered different type of trees such as binary tree, skewed tree, then binary search tree, okay, then complete binary tree, then we have seen extended binary tree, strictly binary tree, okay. In the same way there is a AVL tree, okay. So this is very important tree in data structure. Now why its name is AVL tree? Because it was invented by three computer scientists named Adelson, then Waleski and Landis. So these three computer scientists were developed or invented this AVL tree concept. That's why its name is AVL tree. Okay. So why AVL tree come into picture? Getting? Because there is a drawback with binary search tree. Generally, we are using binary search tree for searching operation or for fast searching operation. Getting? You know that whenever we are searching element inside array. Getting? So what is the worst case complexity of linear searching? Big of n. Getting? This is the worst case complexity with linear searching operation with array. Getting? So consider there is a array of 10 element, and if your element is present at last location, that is at 9th index, then big of n is the worst case complexity for that searching operation. Okay, so we can make that searching operation fast, getting, with the help of binary search tree. So binary search tree is binary tree, getting, which is either empty or it should satisfy three properties. Getting? Which are those three properties? So to understand AVL tree, you should first understand what is binary search tree, because there is a drawback with binary search tree. That's why this AVL tree concept come into picture. Okay, so what is binary search tree? What is binary search tree? So first thing, binary search tree is a binary tree. Binary search tree is a binary tree which is either empty. It means binary search tree can be empty, or it satisfies following three properties. Which are those properties that we'll see? So see, first property is the value of left node or the value of left subtree should be less than the value of root. This is the first property. The value of left node or left subtree is always less than the value of root. This is the first property. For example, suppose 3 is the root, then the left subtree, the value of left subtree or the left children of this particular node should be less than the value of 3. Getting? So this can be binary search tree. This is the first property. What is second property? The value of right node. Or right subtree should be always greater than the value of root. Okay, what is second property? The value of right node or right subtree. Value of right node or right subtree is always greater than root. Getting? So what is second property? The value of right node or value of right subtree is always greater than the value of root. This is the second property. So the right child of this 3 Getting? That is always greater than this root. That is always greater than root. These are the two property. And what is third property? All the nodes, okay, or all the subtrees, left subtree and all the left subtrees and right subtree should satisfy these two properties. Getting? So suppose if this 2 has some left and right subtree, this 4 and 4 has some left and right subtree. So all those subtrees should satisfy these two properties. That is the third property. Getting? So what is third property? All the left subtrees and right subtrees of your tree should satisfy these two properties. These two properties. So this is binary search tree. Now what is the drawback of this binary search tree? As its name suggests, binary search tree, we are using this binary search tree for searching operation, fast searching operation. Getting? So this gives you better what we can say, time complexity as compared to linear searching. Getting? Okay, but sometimes this binary search tree also fails to give the good complexity. Now I will show you an example. Suppose you have such tree. This is also binary search tree. Suppose this is also binary search tree. Okay, so this type of tree is called as left skewed tree. This is called as left skewed tree. Left skewed binary search tree. Getting? This is also left skewed binary search tree or binary tree. Okay, so this is binary search tree. Getting? Now this type of tree is called as left skewed tree because it is growing to the left side only. Getting? It is grow to the left side. Now suppose I want to search 1 in this particular binary search tree. Now what I need to do? I need to do some comparisons. So how I can search this particular node? First I will search or I will compare this node, this particular element with root of the tree. So see, 1 is equal to 4. I will do this comparison, first comparison. Whether it is it true? No, it is false. Then I will check this one with this node. Getting? Whether this operation is true or this condition is true or false? Again false. Then next I will search or I will compare this node with next node. This condition is also false. And what is last? 1 is equal to 1. So see how many comparisons we have done here. How many comparisons we have made here? Again 4. 1, 2, 3, 4. Getting? So how many number of nodes are there in this node? 4 nodes. So again the complexity is big of n. N stands for number of nodes. Getting? So which is very similar to linear searching. So whenever you have skewed tree, it may be left skewed tree or right skewed tree, then again the worst time complexity is big of n. This is the problem with binary search tree. That's why there is a concept of AVL tree. Because such condition will never come in your AVL tree. Getting? Such conditions will never come in your AVL tree. Okay, so what is mean by AVL tree? What is the definition of AVL tree? First thing, it should be binary search tree. Okay, so we have seen 3 properties of binary search tree. The first property is value of left node or left subtree should be always less than the value of root. Second property is the value of right node or right subtree should be always greater than the value of root. And what is third property? All left subtrees and right subtree should satisfy first 2 properties. So this AVL tree should satisfy all the 3 properties of binary search tree. Getting? This is the first thing. So AVL tree should be binary search tree. That is the first condition. And what is second? There is a concept of balance factor. In case of AVL tree. So that balance factor should be either -1 or 0 -1 or 0 or +1. There are only three possibilities. The balance factor of each node in AVL tree should be either -1, 0 and +1. Now what is meant by balance factor, that we'll see. But see, this is the second condition, and this is very unique condition in terms of AVL tree. This was not there with binary search tree. First thing, AVL tree should be binary search tree. Second thing, the balance factor of every node in AVL tree should be either -1, 0 or +1. Only three possibilities are there. Now what is meant by balance factor? What is meant by balance factor? So see, the formula is that the height of left subtree, height of left subtree minus height of right subtree is called as balance factor. So balance factor is nothing but height of the difference between height of left subtree and height of right subtree. Okay, so balance factor is equal to height of left subtree minus height of right subtree. Now you already know what is meant by height of node, getting, and height of tree. So we'll see that. So getting the definition of AVL tree. AVL tree must be first binary search tree, and the second condition, the balance factor of every node in AVL tree should be either -1, 0 or +1. Getting? And what is meant by balance factor? Balance factor is equal to height of left subtree minus height of right subtree. Now we'll revise what is meant by height concept. Height of node or height of tree with the help of example. So consider suppose this is binary search tree, and suppose I want to find out the height of 3. Getting? Height of 3. So height of node. First definition is what is height of node. So what is meant by height of node? Getting? We already seen this. Height of node. Consider height of node X. So it is the number of edges. It is the number of edges in longest path. It is number of edges in longest path from node X to leaf. It's a leaf. This is the height of node X. Getting? Definition. Number of edges in longest path. There may be number of paths available. Getting? To reach to particular leaf. Getting? From that particular node. But we should consider the longest path. So number of edges in longest path from node X to leaf. So consider this 3. Getting? So see, height of this 3. What is the height of 3? So what is the definition of number of edges in longest path? Now here there is only one path. There may be multiple paths available, but in this tree only one path is there. Okay, to reach from this 3 node to its leaf. So this is path. And how many edges are there? 1 and 2. Getting? 1 and 2. So height of this 3 node is 2. Height of this 3 node is 2. Getting? So that is the height. Now what is the height of 2? Height of 2 is from number of edges from this 2 to its longest leaf. So here only one leaf is there. So height of this 2 is 1. Height of 2 is 1. What is the height of 1? Height of 1 is 0. What is height of 5? 0. Now what is height of 4? What is height of 4? Now see, there are 2 paths available here for its leaves. So there are 2 leaves for 4. First one is 1 and second one is 5. There are 2 paths. Getting? So which path we should consider? The path which is longest one. Getting? So see, first path is 4, 3, 2, 1. So how many edges are involved in this path? 3 edges. 1, 2, 3. So this is the height. Here only 1. So we are neglecting this. Getting? We are neglecting this path because this is not longest leaf or the path. Getting? So we are considering this 3. So see, height of this 4 is 3. Getting? There are 2 paths from this 4 to its a leaf. This one and this one. We are considering the longest path, that is 3. So height of 4 is 3. Getting? And 4 is root of this tree. So height of root is also height of tree. So what is height of this tree? 3. Height of root is 3. So that's why height of tree is 3. Getting? Okay. Now balance factor. Getting? Balance factor. So what is the balance factor of this one? So what is the definition? Balance factor equal to height of left subtree minus height of right subtree. Is there any left subtree for this one? No. So what is height of left subtree? 0. Getting? And what is height of right subtree? Again, there is no any right subtree, so 0 minus 0. So again 0 is the balance factor for 1. Getting? Now what is the balance factor of 2? What is the balance factor of 2? So what is the definition? Height of left subtree. So what is height of left subtree? Getting? From this node to its longest leaf. Getting? So 1, only 1, and right subtree again empty. So 1 minus 0. So what is balance factor? 1. What is balance factor of this 2? 1. Next, what is the balance factor of 3? What is the balance factor of 3? So balance factor is equal to height of left subtree. What is height of left subtree? 2. And what is height of right subtree? 0. So 2 minus 0. So 2. 2 is the balance factor. Getting? What is balance factor of this? See, 1, 2, 3. 3. That is height of left subtree. And what is height of right subtree? Only one edge is there. So 1. Getting? So what is the balance factor of this 4? 2. 3 minus 1 is 2. So balance factor of 4 is 2. And what is the balance factor of 5? 0. Height of left subtree minus height of right subtree. There is no left and right subtree for 5. So 0 minus 0, 0. Getting? So these are the balance factor of nodes. Now just check whether this is AVL tree or not. Just check whether it is binary search tree or not. Yes, it is binary search tree. See, 1 is less than 2, 2 is less than 3, 3 is less than 4, and 5 is greater than 4. Getting? This is binary search tree, but this is not AVL tree. Getting? AVL tree should satisfy both conditions. First thing, it should be binary search tree, and second thing, the balance factor of each node in that tree should be either -1, 0 or +1. Here this node satisfy, this node satisfy the condition, this node satisfy, but these two nodes 3 and 4, these two nodes violates the balance factor condition. Getting? So balance factor of 3 and 4, that is 2. Getting? So 2 is not acceptable. 2 is not the possibility of our balance factor. So this is not AVL tree. This is not AVL tree. Getting the definition of AVL tree?